Hi folks, so here's the second video in this installment. In this particular one here, this is going to go into the actual examples of using the various methods in the for the attack disk and the speed side, various things to compute. I'm going to start this video off, or start this series off rather, this series of videos in Wolfpack itself, starting to look at some of the basic functionalities of the attack disk and the speed side, and then we'll move on to more complex things as the video series goes on. So the first and foremost here, I'm in tutorial. I am going to use that's some chicken scratches here, but I am going to use in contrast to my other videos where I don't show the solution until we're done. I'm not trying to prove any particular type of data gathering in this one. I'm simply just using the tools, assuming that these values have already been derived by some sort of other method, plotting method or whatever. So we're going to use the speeds that we see in here and the angles on bow, and we'll re-derive these figures to a certain extent in some cases, or we'll use these figures in other cases to show the use of the disks. So we'll take this heavy tanker here for an example, and we'll use the first functionality, really the most basic functionality, and that is the attack disk side of the historical attack disk side, the functionality of converting of deriving true course from angle on bow, and then we'll talk about the reverse of that, deriving angle on bow from true course. So the first thing we'll do to derive true course from angle on bow, okay, you would say, and I'm just going to go down to the attack scope here, just because we have a bearing ring we can read off. I should have set my course to 263. Let's just check that right now. Excuse me, 6 degrees. 263 was on before, but 6 degrees. So the first thing we do is we set our own course to 006, and that's aligning the compass rose with this white triangle here. That's 6 degrees there. So that's the very, very first step, no matter what you're doing in here. The second one is, let's say we're observing this target right here, and we estimated his angle on the bow to be 109, and look at that, we're spot on. Okay, so we say, so I'll just go up to the attack scope here, and we say, oh, I see that, let's say we haven't figured out their course yet. Say we're just kind of eyeballing it, and we want to know the course. So we say, okay, all right, I think that's angle on bow left 109, okay, and the bearing is 46 degrees. Okay, so I go in and I set 46 degrees. You can either use this one or this one. This is, whoops, or this one here. This is truly the bearing dial, or the bearing arm. So I say 46 degrees is the bearing. So I set the bearing to 46. Okay, and I said I estimated the angle on bow to be, oh, let's say it's 108. Okay, it was 108 degrees, or yeah, let's use 47 and 108. Okay, so 47. It's going to be ever changing here, but that's okay. So 47 and 108. So then I take the target disk, and I know the angle on bow was left, or port. So I say, and I align the angle on bow with the bearing line here. So 108 there. Okay. And the target bearing is 47 here, 108 there. So the true course is showing as 341 degrees. Now let's check that. Okay, 341. Yep. Okay, that's about right. Okay, 340, 341, somewhere in there. Okay, so that's that. So then the other example is if I laid a couple of lines out here. Okay, so let's say we're overhauling this target here. His course is, we've plotted this over time. Okay, and it's 020. We say, okay, we fared the course line. We think it's 020. It's like, okay, well now I've got a good course, I got a good speed on a target, but I need to get that angle on bow that corresponds to that course into the TDC so that it's set and we don't need to worry about it. Okay, so let's say we've observed a bearing of, let's say, just for argument's sake, this is about 280 degrees, let's say, or about there. Okay, so that's just for visual reference there. But say 280, so we know we're on course 006, and we know the target's course, so we've got 006 as our own course. We set the target course to a known value 20. Okay, and we set the bearing of 280. That's the bearing that we just measured. So we drag that over here. 280. Okay, that's here. Boom. 280. Now look at that. Here's the angle on bow. It's right 86. So we'd say, okay, TDC input. You would keep that scope right on that bearing, or the optics right on that bearing that you observe, and you'd say, okay, set TDC angle on bow right 86, and then you're done. So then it's in. Okay, so that's the second piece. Those are the two big functionalities, very common functionalities of the attack disc that everybody kind of knows about. That knows about the attack disc is those particular things. Okay. So now we'll get into more of the complex areas here. So I'm going to just reduce our speed a little bit down to slow ahead here, and then we'll start using the speed side of things here. So here's the speed side. The next one I'm going to demonstrate is calculating angle on bow from aspect ratio. Now, those of you who aren't familiar with this method, what it essentially is taking the aspect ratio of the target, and what that is, that means is the length of the target divided by its height. Okay, that gives you a ratio. It's called aspect ratio. And then you measure the target in the scope as far as its width in centiradians and its height in centiradians. Okay, and then you do that division, and you compare those two figures to derive angle on bow. Now, to demonstrate the formula, just in the map here, we'll get it laid out. So it's the arc sine. Okay. Just gonna type or not? Okay. Of aspect ratio observed divided by aspect ratio actual. Okay. The inverse sine, okay, of the aspect ratio observed over aspect ratio actual. That will give you, now, whoa, what's going on here? Inverse sine, we didn't talk about that. Well, in terms of the functionality of the attack disc, of the speed side, excuse me, all you're doing is starting from the end and working your way back, and instead of doing division, you're doing multiplication or vice versa. So if you see this, a formula that says the inverse sine, just start with actual times observed. So how does it look in practice? So first and foremost, I need to derive the actual aspect ratio of the target. So I've already identified this guy as a heavy tanker type 12. Okay, and I'm going to use his actual mast height, his length of 150. So I do division. I take 150 length divided by 28 mast height to get his aspect ratio. I can do that with this. Okay, all I have to do is remember this is division, and I can use this as the integer, as the denominator for the mast height integer. And I'll have to interpolate a little bit here and say 28 is about 25, 26, 27, 28, maybe right about there. Line it up with a 150. Again, here's moving the decimal place over. It's 1500. That's 150. Okay, and at the reference line here, I read off the aspect ratio. And again, moving the decimal places. 5, 5.1, 5.2, 5.3, just a hair over 5.3. So we'll just call it 5.3. Okay, 5.3 is the actual aspect ratio of the target. Okay, so that is here. That is going to be, whoops, that is going to be 5.3. Okay, that's right there. All right, and then just to put the division in here, and now I have to get the, oops, that didn't work. I have to get the observed now. Okay, so now what I do is I say I measure length. Okay, and the length is going to be about 10, 11, 12, 13, 14, let's say 14.6. Okay, so 14.6 divided by height, which is here, and the height is 2.7. Okay, divided by, forget the m, that was just me, 2.7. Okay, 14.6 divided by 2.7. Now I can do this. If I move the decimal place over 1, I can do that right in there. So 146 divided by 27. 146, I pick 27 out, which is right about 7, right about there, over 146, which is here, and I read that off. That's 5.1, 5.2, 5.3, 5.4, 5.44. Okay. So observed is 5.44 divided by 5.03, the inverse sign of that. So what do? I want to do inverse, so I want to start here and do multiplication instead of division. So I take the 5.3 times the 5.44. So what do? I take the 5.3 and set it to 90. 5.3, let's use this style now. 5.3, 1, 2, 3, set it to 90. Okay, we're doing division by 1, meaning we don't want to change the value. 5.3, set it to 90. Okay, now I want to find the degrees on the outer scale that align with 5.44. So the degrees that align with 5.44 are 5.1, 5.2, 5.3, 5.44 are here. Now you can see we're in this this other range here. This is 6, just under 6. So 5.44, and I can use this as a reference here. 5.44 right there. So it's just a hair under 6 degrees. Now that's 6 degrees on the other side of 90. Okay. So what is our angle on bow? Or actually, to do it better, we might be better off by, since we're past the 90, align 5.44 with 90 itself, okay, and then read off at the other one so that it gives us a better answer. 5.44, aligning that with 90, and then reading off the angle on bow at the other one going the other way, because we were past the 90, and we'll read it off at 5.3. So now at 5.3, which is here, 5.1, 2, 3, I read off 75, 76, 77. It's about 78. So that if I take, now that's not 78 because it's on the other side of 90, right? It's actually, the angle on ball is over 90. So if it's 78, okay, so 90 minus 78 is 12. So then I would take 12 plus 90. I'm on 12 degrees on the other side of 90. So when we measured that, the angle on bow was 102. 90 plus 12 is 102. Now we've moved a little bit since then. His angle on bow has gotten a little less, but it was about, back when we did that, it was about 112. Okay, so so now to take that a step further, I should have noted the bearing there without changing the scope, but you could go in and say, okay, 112, and then go back and derive the target's true course from that. Okay, so that's how to derive from aspect ratio from this. There's a couple different steps, but you can, of course, you can use a calculator if you want to get the aspect ratios, but to get these here. But you can also just know it's not obviously not as exact, but you can use the disk division and multiplication in the disk or division rather to derive those as well. It's all just going to show that most everything can be done with this here without having to do anything outside. So I would have not moved my scope at that while I was doing those calculations, okay, and then gotten that 102 degree angle on bow, and then I would have noted the bearing, noted my own course, as we demonstrated before, input all of that into this side, gotten the target's true course from that. Okay, so based on setting the angle on bow, as we showed before. So that is the method by which you would do that. So so again, I will. Why don't we go ahead and just get? We'll make like we're going to shoot this particular target here. So let's just say we're doing an overhaul maneuver. We'll just do a little truncated one. You're obviously not going to be overhauling from 3,000 meters away, but just for the sake of keeping this quick and just demonstrating the principles behind it, let's go ahead and just do that. So I'm just gonna match his course. His course is 340, and then we will do a little overhaul here and just show how we would go about setting the attack disc. Getting the angle on bow. Getting the target's course, computing the angle on bow off of that, and setting it into the TDC, etc. So 341, okay, so that's about right there. I need to go into the attack disc and set 341 now, update the course. So there we go, 340, I said 340. Okay. So now let's go ahead and get the information set into the attack disc, and therefore get it also set into the TDC. Oops, I didn't want to go all the way up here. Look at that. Breath of fresh air. Okay, so then we get down. I'm just going to set this to attack periscope. Okay, and then let's go ahead and we know his course is 340. Let's say we've already plotted that. Okay, so I've already got my own course set here of 340. Next step, of course, is let's just use that bearing right there. That's 86. So I go, I set the bearing here, okay, to 86, which is right here. Right? So that's set, and the target course I set. Let's get this out of the way. So target course is 340 as well. We matched his course. So at that bearing right there, the angle on bow is port 94. Okay, so then without moving the scope, I'd say TDC set port 94, probably without that much enthusiasm, but you get the point. Port 94, so we say, okay, there's 1, 2, 3, and 4. That is set. And alright, so then say, okay, we're doing our overhaul maneuver, and we've already got that set in there, so we're in good shape, okay? Let's just also, okay, so that's good. Okay, so then now the TDC, or the angle on bow is set in the TDC. We don't have to worry about it anymore. They don't change course in this game until they detect you, so that is good. So the other thing, okay, we've got that set in there now, but wait a minute now. We did a plot, right? So we plotted. Let's say we plotted this guy. Now forget the 6.5 here, just for argument's sake. Let's say we plotted this target. 340. Okay. This is our plot of him, and we're overhauling him right now, okay? And we took a couple different bearings. Boom, we plotted them. We did our diligent little plotting here. We got these bearings here, and then, these were our ranges here, okay? And then we plotted this over time like this, okay? So let's say these were 5-minute intervals. We say, okay, at 0, 5 minutes, 10 minutes. All right, so let's see what kind of speed we have here. So in order to derive target speed over a particular distance, you can use this thing, or you can use the attack disc. So I measure the distance. So I say, all right, I know it was 10 minutes. The distance is 2,300 meters. Right? So 2,300 meters or 10 minutes. How do we figure that out? Go to the speed side. 2,300. We find it here. We find 10 minutes here. We align, do division. So it's speed equals distance over time. Distance over time. We align those two there, and we go over here, and at the reference line we read the target speed off, 7.4 knots. Okay. Now I just use that as a hypothetical example. Of course, the target is going 6.5 knots, but I didn't want to back into the right distance or whatever. Just to use, it's not the way you're going to be doing it. The way you're going to be doing it is likely plotting and then having a distance and saying, I know time and I know distance, I know time, so let's give me speed. Essentially the same thing that this does up here, just a little more precisely, or maybe, I don't know, I think user friendly. But anyway, so that is the other calc that I wanted to go over in this video. So we've got, just as a recap, those will be the first ones for this first video of the series. Recap, we covered converting true course, or converting angle on bow to true course, or I should say deriving true course from angle on bow, deriving angle on bow from true course, as well as computing angle on bow based on aspect ratio. Okay, that's this. And we also covered the fact that, just remember, typically with typical multiplication, typical sine function like this, you'd work from left to right, and I'd say aspect ratio observed over aspect ratio actual. Well, one thing to note is that actually doesn't work in this, because both aspect ratios are on the same disk. You can't divide one by the other. So the workaround of it is that you work from right to left. Since you're taking the inverse of the sine, you work from right to left, and you do multiplications to division. You take your actual, okay, and you align that with 90. You always align, when you're doing multiplication, you always align one value with 90, and then read the other value off. To the extent, and this is what happened to us, to the extent that you align that value with 90, and all of a sudden your answer, that's your other value that you're referencing, is over 90, just use the other one at 90 and read backwards. Okay, you arrive at the same place. That's really, I guess that's really all there is to say about that. Those and then speed over distance. That's purely division. So you're doing your plotting long range. You're deriving a distance, and you've got a time interval there, so you can just use time, speed, and distance to figure out the target speed by doing simple division with the slide rule, which you just think of it distance over time. Like, what's the distance over time? I mean, you can even say that in plain English, like, what's the such and such amount of distance over time. Distance over time. So literally distance over the time gives you the speed. One thing to note about this, and those of you who are familiar with using an E6B, for example, slide rule, they tell you when you use that, that the pointer always points to a rate. If it's an E6B, whether that's fuel consumption or whatever the case is, the pointer will always point to a rate. Well, a rate is speed. Speed is a rate. So you'll notice the common thread through all of these methods is that whenever you've got a calculation that's saying, look at the reference line and read off the value, it's always reading off of a rate, and that is a speed in this case. So that's also an important thing to remember, is that the pointer will always point to a rate. Whenever you're deriving something from a reference line, it's always going to be speed. Right, so with that, I think that'll cover this one, and the next one we'll get into a little better position, and we'll do a couple more things to do some kind of double checks on speed. That's kind of the next thing on the docket. So I will start that in a minute.